Logarithmic functions are the opposite of exponential functions. In particular, log base a of x is the inverse of a to the x. What does that mean? Well, let's think of two functions that you're more familiar with that are inverse pairs of each other. Y equals x squared and y equals square root of x. At least when x is positive. Let's assume x is positive so we can take the root. These are inverse functions. Each is the opposite of the other. And that's useful because if I have y equals x squared and I want to write down what x equals, in this case, then x is equal to the root of y. If I have y equals 2 to the x, and I want to write down what x is in terms of y, if I want to rewrite this, then I need some kind of notation like the square root that tells me how to do backwards exponents. And the answer is log base 2 of y. Let's use this in a particular example so that it makes a little bit of sense. I have y equals 2 to the x, and I tell you y equals 8. Then what is x? Well, you might think, okay, 8 is equal to 2 to the x, so x is going to have to be the exponent. That gives me 8, so that's 3. 2 to the 3 equals 8. Another way of writing that is that x is equal to log base 2 of 8. And this you would interpret as saying the power of 2 that equals 8. What power of 2 equals 8? And the answer is 3. So you'll have to see a few examples of these before you become fluent in the language of logs. Let's do some. Log base 3 of 9, that's asking you, what power of 3 equals 9? Log base 3 is a machine. You put in a number and it outputs the exponent that you'd have to put on 3 to give you that number. The exponent you'd have to put on 3 to get 9 is 2. Let's do some more examples. The exponent you'd have to put on 3 to give you 3 is 1. What exponent would you have to put on 3 to get 1? The answer is 0 because 3 to the 0 equals 1. If you have any number and you want b to the something equals b, that exponent is always going to be 1. So log base b of b is 1. Similarly, b to the what equals 1. For every number b, the answer is 0. So again, logs are the inverse process of exponentials. Would it make any sense for me to write log base 2 of 0? That's like asking you what power of 2 equals 0. And there is no power of 2. That does not exist. It's undefined. Likewise, log base 2 of a negative number doesn't make any sense. You can't have 2 to the something equals negative number. So what we're saying here is that the domain, stuff you're allowed to put in this function, is all positive numbers. Let's use that fact to make a table of values and draw the graph of log base 2. Here's the graph of 2 to the x, just so we can compare what the graph of log base 2 of x equals. So make a table of values. If I put in 1, I can't put 0 or negative, so I'll start with 1, 2, 3, 4, 5, 6, 7, 8. I'll write down these values fairly quickly, and you can double check them on your own. Log base 2 of 1 is 0. Log base 2 of 2 is 1. This will be some decimal number I'm going to ignore for now. Log base 2 of 4 is 2. These are going to give me funny decimal numbers. Log base 2 of 8 is 3. Again, you should stop and double check that all those numbers make sense. So I get the point 1, 0, 2, 1, 4, 2, 8, 3. Those are points on the graph. So let's plot those. And 8, 3 will be off the charts. It'll be somewhere like that. So I can connect up these dots. And it would go on down like this. And hopefully you might notice that, like all inverse pairs, these two graphs are mirror images in this diagonal line y equals x. If there's a point 2, 1 on log base 2, then there's a point 1, 2 on 2 to the x, because they're inverses of each other. All log graphs look more or less like this, just with different steepness. In calculus, we're going to be most interested in log with base e. This is such a special function that it gets its own name, its own notation, and its own video.